I forgot that. Yeah, now it works. Okay. Now another thing that we say is that the transition matrix is row stochastic. That means all entries are between 0 and 1, right? And all rows sum up to 1, and that's also kind of clear here. That means one row here is simply the probability to step from this. In this example, would be the probability to go from state 1 to any of the states 4, right? So this is from state, and this is to state. So I go from state 1 to 1, 2, 3, and 4. And of course, the probability must sum up to 1, because if I start in one state, I end up I must end up in any other state. So this probability must sum up to 1, whereas this probability does not have to sum up to 1, right? So the probability to reach one state does not have to be. So there might be states where I don't have to be necessarily, right? This is the difference. Yeah, this is the observation already. Now I can, if I write a state here like this with a row vector pi, right? Pi is simply the probability to, first there's initial probabilities here, right? Initial probabilities pi 1, pi 2, pi 3, and pi 4. And if I write this as a row vector, then I can write this whole thing as then the next pi, this is pi 1 and pi 2, sorry, pi 1, pi 2 is just pi 1 times a, right? Computed as a row vector times this, right? This is just the probability to reach that state is just the sum over the probabilities to come from any of these states times the transition to reach from that state to that state. That's just this times the probability plus this times the probability to reach from here to here, which is nothing else than a row times the first column of A. Right? This makes things a bit easier because then we have a vector representation. Okay, so this is how we can write this, right? For every pi k t, t is the time and k is the state. We have this expression here, and we can write this more in a cleaner way using this matrix notation here. Now, the first thing that we have to know or understand here is what is a stationary distribution. Now we're talking about distributions, and distributions means that for over all the states I have some probability, right? And this, at every time step, I have some kind of distribution, and this is the pi t at every step. So we say that pi t is stationary if the distribution from here to here does not change, right? So I apply A, and that means if I do this thing here, right, I apply A to pi, then the pi before and the pi after are exactly the same, right? Pi t equals pi t minus 1. This is an important notion because that will then be used. Stationary distributions are the key element to build a Markov chain Monte Carlo method, right? Later the idea is this will be our target distribution where we like to sample from, and we like to find A matrices so that pi is stationary. The first question here is, how can we know that a stationary distribution actually exists, right? And the second one, if it exists, do we know that it is actually unique? The first one is the existence. To find a stationary distribution, we can think of this as an eigenvector problem, right? Because this is basically, we can write it a little bit different here. We can say, let's say we have a vector v, and v is an eigenvector of the transpose of A, right? Let's say we have that, and let's say we have an eigenvector to the eigenvalue 1, right? If we find that, then its transpose is simply pi, right? Because now if we put vt here, then we would have exactly this thing here, right? Then this solves this equation here. Hope this is clear. So if we have AT V, if we now say VT is, that means if we compute this here, AT V, sorry, we say pi A equals AT pi T, and this is AT V, and this is V T, and this is pi, right? V pi T, sorry. Well, that doesn't matter because in general, this is what we mean, what we want to do, right? We would like to find an eigenvector to A to the eigenvalue 1. And there's this theorem, Perrin-Frobenius, that says every row stochastic matrix has such an eigenvector. The problem is that this vector might not be unique. Right? So you might have many of these eigenvectors to the eigenvalue 1. But that's nice, okay, because that can, at least we can say there is something like that, so we can find such an eigenvector. And now to define uniqueness, this is just an example where this is not unique, right? Here we have, again, these numbers here are states, right? This is not variables, this is states. And these transitions here are just probabilities between the states. And you can imagine that if you start in this state and you jump into the other state with probability 0.5, and then from there you jump into this one with probability 0.9, then you can think this is like, you can write this like in a similar way as this diagram here. But you can also already see that there's two places that you might end up with, and once you end up in one of these places, it's impossible to reach another state. So if you start in 3, and once you're in 4, right, you will never go out of 4 because the probability of going into 4 is just 1, right? You always stay into 1. You will never go out of the state 4, and the same here, right? Once you're in one of these two states, you just jump around between 1 and 2, but you will never get back to 3, right? That means there's two kind of stationary distributions, two, let's say, holes where you can end up when you start in this state. And this is a problem. You don't want to have these kind of Markov chains. And so one sufficient condition to have a unique stationary distribution is that you can reach every state from every other state in a finite step and with 0 probability, right? So this is not the case here, of course, but if this was the case, if we could reach every state of these 4 states from every other state with non-zero probability in a finite number of steps, then you call the chain is ergodic, right? And then you can show that ergodic chains, they always have a stationary distribution, a unique stationary distribution, right? This is the sentence, the theorem, right? Which is not proven here, but this is something that it's important to know, right? It's an important theorem. If the chain is ergodic, then you have a unique stationary distribution. This is equivalent to the property that the transition matrix is irreducible. You can imagine that this is kind of the same thing. Irreducible means that for every entry in this matrix Ij, there exists an m, so that if you apply a m times, then the probability is not 0. This is basically the same. Of course, I haven't said this. So if you start in state 1, or in this t minus 2, and go over through the time steps, then applying a to this p, you can do this multiple times, right? So then you would say in the next round, this is pi 2 times a, and this is just pi 1 times a square, right? So this is just how you express the number of steps in time. So if you start in this state, after a number of steps, you might reach this state here, right? It might not be possible to reach this state directly, but after a number of steps, you reach it. And this is what you need to guarantee that the matrix is irreducible. That means for every pair of states, there is some step m, right? So that you can reach it with non-zero probability. Right? This is how you read. So a to the m is just, this is the number of times you step, right? This would be then m. And then if you step m times, then eventually you can reach every state from every other state with a finite, with a non-zero probability. Okay, so this is just another way of expressing ergodic. Okay, now why do we do all that? The main idea of MCMC is now to find a transition matrix, yeah, so that a given distribution is a stationary distribution under that transition matrix. So it's kind of the opposite that we did so far. So far we specified the transition matrix and we looked at, is the according distribution that it produces, is it a stationary or not, and is it unique or not? But now what we want to do is we are given pi already. We have a distribution and we want to sample from it, and to be able to sample from it we need a nice transition so that the Markov chain is, so that this distribution is stationary under this transition matrix. Right? This is kind of the opposite of doing that. And to do that, we need some criterion that tells us that the distribution here we have is stationary. And one sufficient condition to that, we'll see this later, is the condition of detailed balance. And detailed balance is defined like this here. So we have, this is another example of the three states. A transition distribution pi t satisfies the property of detailed balance when this is the case. So it's kind of just turning things around, right? This just means for every state pi I, right? If I apply that pi I to transition j, then this is the same as if I started in j and go from j to I, right? So this is the condition that has to be held. If this condition holds, then we'll see then pi is stationary. And this is just the example, right? So this is we start in pi 1, we transition from pi 1 to pi 3 with A13, right? This is the A13 that we apply. And of course we have the others, right? We have all the others here. But this is the same as going from here to here, right? If that's the same thing, then we call this that pi t satisfies the property of that detailed balance with respect to A, right? And again, now the trick is to for a given pi find an A, right? So that it's the detailed balance is the property is met, right? We also say that the chain in this case is reversible, right? And now this is the main theory and a very simple proof that this actually works. So if a Markov chain with transition matrix A is irreducible, and we think that for now we assume that this is always the case, and if it satisfies the detailed balance with respect to the distribution, then pi is a stationary distribution of the chain. And the proof is very simple. If I can swap things here, right? What I actually do is I transpose A basically, right? So if I for every state pi I, if this is true, right? This is the definition of detailed balance. Then the interesting thing is I can now pull out pi j in front of the sum, right? Because it's independent on the sum, and this here is now I'm summing over the column, but I transpose A, and we know that A is a stochastic matrix. That means the sum over the transpose of the column of the transpose must be 1 because this is basically the row of A. Right? Here I'm summing over the row of A, and this is 1. Right? So in this case, it directly comes out of the definition of detailed balance. That means then, in that case, if this holds for A, then pi is stationary. Right? This is a very simple proof. It's sufficient but not necessary. Right? So there might be other cases where we have a stationary distribution, but this is, for us, it's sufficient. Right? If we find out an A that holds that, then we're happy because then we say pi is stationary, and that's what we want. Now, how can we use that to sample? Now, the idea is to use, again, a proposal distribution. That's the same as we had last week with the reduction sampling and with the importance sampling. So we have some proposal distribution Q. And then in the MH algorithm, Metropolis-Hastings algorithm, we use that Q to define a transition probability which is like this here, right? And so I think what the next thing I should just do is just show the algorithm. So this is it's a very simple algorithm. It's amazing how this works and that it works. So what I do is I first initialize x0 as one sample. Then I have a number of like a for loop that says at every time step or number of samples. Now the current sample is just x. And now what I do is I use my proposal distribution, which is simply the transition probability from x to the new state, right? I just have some proposal that says, given I'm in state x, what's the probability to reach x prime? And I sample from the distribution, right? So I sample a new state. And now the trick is to compute a so-called acceptance probability, which tells us if we remain in that state, or if we don't remain in that state. This is again like the same as rejection sampling. So we are not yet here. We want to stay in that state, but we don't have. So in the same way as rejection sampling, we still need to show if it's worthwhile staying in that state, kind of, right? This is kind of the way you can express that. And to do that, we compute this value here. And I have to explain what pi tilde is. Pi is our target distribution. That's the distribution you would like to sample from. This could be any distribution that you just give. And pi tilde is its unnormalized version of it. The reason why this is unnormalized is just to make it even more general, right? So pi tilde doesn't even have to be a proper distribution. It doesn't even have to sum up to 1, right? It can be any function here, because we have a fraction here, and we have pi tilde on both sides, right? That means if we want to have a distribution, then we would have a normalizer here, but the normalizer would cancel out because it's the same over in both, right? That's the trick. So we don't even need a proper distribution to sample from. P can be something which is not normalized. But again, to compute this here now we have two samples, an old sample and a new sample, right? X and X prime. And now we sample this value here, and we compute the minimum of this value with 1. This is R, right? This is our acceptance probability. Now we sample between 0 and 1, and we look at, is our sample smaller than R or is it not, right? And if it's smaller than R, then we keep the sample, and otherwise we reject the sample. This is very similar to rejection sampling. That is very interesting. Now the big question is, why does this work? And the answer for that is actually quite simple. So first of all, what we have to consider is, what is the actual transition probability now of this algorithm, right? What is A in this case? And it turns out that A is nothing else than our proposal times this alpha value, right? So we can think of the matrix Aij, or we can also say Ax prime and x is the same. No, sorry, x prime. So this is from this state to this state, right? This is I start in state x and I go to x prime, which is same as q of x prime given x, right? Again, this is the opposite. I start in x and I go to x prime times alpha of x prime and x, right? This is the alpha value that he computed here. And how can we understand that? Well, this is basically exactly what we do. This is the probability of reaching state x prime, and this is the probability of staying in x prime. So we have to multiply them both. We have to say first, how likely is it to actually reach x prime? And once I'm here, how likely is it that I actually remain there? And this is this one here, right? And now we just plug in the definition of alpha, which is min of 1 and Sorry, is that right? Yes. I think I'll pi tilde. This is probably not. This should be R. Anyhow, so this is min of 1 x prime q x given x prime divided by pi tilde x times x prime x, right? Yes. So I just copied alpha here, and this is the R. R is actually the probability to stay in the state, not alpha, right? So now this is our transition, and what we have to show now is that this transition fulfills the property of the detailed balance with respect to pi with our the p with our transition. That means p of x prime. Sorry, p of x times a x prime, right? This should be the same as, we want to have the same as the opposite, p of x prime times a of x prime x, right? We just switch things around. This should be just the transpose of a, and this should be the x prime, right? If this is the case, then we know that detailed balance is fulfilled, and then we know that our pi p is a station distribution of our Markov chain, right? And that's very simple to show. We just plug this in. We just say this is pi of x times q of x prime given x times min of 1 and all that stuff here. Qx given x prime divided by pi qx prime x. Right? I just pull this in now. So this is the same as min. And now this is very simple. This and this cancels out. And what remains is I remove the tilde. That's a little trick here. Why is that? Well, this is p times the normalizer. This is p times the normalizer. I cancel out p here. And that means p stays in the, right? Is that clear? So here, this is p times normalizer, and so I put the normalizer back in, let's say, on both sides, and then I cancel out p, and I cancel out q, right? This just cancels out, and the enumerator remains, and now the very simple trick is just switch things around, because minimum is symmetric. This is the minimum of I think there's a prime missing. Yes, there's a prime missing. Q of x given x prime times p of x q x prime given x. Right? I just switch these things around because it's symmetric, and now I can express it in the same way as before. Right? This is p of x prime times q of x given x prime times minimum 1 of p of x q of x prime given x divided by p of x prime q of x given x prime. And this is the same as p of x times a of x prime x. Very simple trick, right? So this means that our A now is chosen, right? We have chosen the nice A because it fulfills the property of detailed balance with respect to P, and P is our target distribution. And now we have not specified P at all. This is just any distribution that we want to have, which means that the algorithm now can sample from any distribution. Yes? The alpha. Yeah, it seems a bit kind of a made-up thing, right? So it's hard to like interpret this. It's just a ratio. I don't know how to give it like a bit more visualization thing. I think it's just chosen very neatly so that the computation is easy, right? I'm sure there are other ways of like understanding it in a bit more detail. I think it's sufficient to understand that this is just a nice way of doing it, right? Because then it turns out that my transition probability that actually turns out is so nice, right? Right. So combined with the proposal distribution Q, right? I have now two distributions. One is Q, and one is the probability R of remaining in the state. If I multiply them both, then I have a very nice transition probability, right? And this combination of these two gives me the transition probability so that P is stationary. Another just a little side note here, that all these formulations are valid also for continuous variables. We did this for discrete variables, but this also holds in the continuous space. Now, one important question is how to choose the proposal distribution. And the proposal distribution is very important to have a correct one, a valid one, particularly because you need to be able to reach every state from every other state, right? If you have a proposal distribution that doesn't reach certain states, then this doesn't help you much, right? Then you would not cover the whole state space, and then you would not be able to sample accordingly from that state space. So you need something that gives a non-zero probability of moving to the states that have non-zero probability in the target, right? Of course, if you have states that are never reached anyhow in the target distribution, then you don't need a proposal that goes there, right? Because you will always reject that because you will never actually remain in that state. But for general case, if you don't know what the target distribution is, a good proposal is the normal distribution, Gaussian distribution, because it has a non-zero probability for all states, right? The Gaussian distribution has a very low probability, but it's never zero, right? It's very, like, there's always a remaining probability to reach certain states. However, it's very important to choose the right variance of this Gaussian. So it's really important, how wide the Gaussian actually is, because there's this trade-off. With low variance, the sampler does not explore sufficiently. That means it is fixed to a particular mode, right? So, so if you stay in one state, and if your variance is very low, then it's very likely to remain in the state, right? You will never, or very seldom, will you just jump out of the state and come to another state. But if you have too high variance, then the proposal is rejected too often, right? Then it happens that you jump very often into some spaces where this is rejected. This is just an example of how this looks like. So the target is now a mixture of two Gaussians. You see the red curve here, which is the target distribution which we'd like to sample from. And the proposal is a Gaussian with different variances. So if you have a low variance, then you stay here, right? You almost always stay in that state. Which means that you sample from the distribution, but you sample only from one of the Gaussians, right? So it's like really you don't explore well because your variance that you use here for the proposal distribution is too low, right? It's just almost completely unlikely to leave the state here and to also sample from the other Gaussian, right? And in this case, you have too high a variance here from the proposal, and that means you very often jump out of the space, and then you remain in that state very often. This is when you have these long trails here, where you have just a number of times where you just stay in the same state because your proposal was rejected, right? And in this case here, this is a way where you can have like a good. This is a good choice for this particular example, and you see so this blue curves here in the end is the histogram that you get from the samples here, right? If you just squash all these samples that you get here together, right? This is time, right? This is the time axis, and along the time axis you get all these samples here, And if you plot a histogram of all these samples, then you get the blue curve. And you see that the blue curve is very, very close to the red curve, which is good, because then it tells you that you have sampled well from that distribution. Okay, let's have a break. Okay, we have had so far the Markov chain Monte Carlo method, and now we have another one which is very simple, and it turns out to be a special case of Markov chain Monte Carlo, which is the so-called Gibbs sampling method. Gibbs sampling, before I start, I just show the algorithm, which is a very, very simple algorithm. Here we assume that we have a number of variables, a number of random variables that we sample from. So every random variable is indexed here with an I from 1 to m. So we have m different variables. And now we have this big loop of t rounds where we sample from that. And in every round, what we actually do is we sample from what we call the full conditional. And the full conditional is simply the probability of one variable given all the others, right? And the trick now is that the state of these variables that we condition on changes with every sample. That means once we have sampled from the first variable, right, we use that variable that we sampled from and plug it into the next round of sampling, right? This is already Z1 the tau plus 1, which is already the very recent sample that we got from here, right? We just put that in here, and in the next round we sample from the full conditional, but now with the new samples put in here, right? This is the whole idea, right? The very simple algorithm, and it turns out that this works also very well, and it's a special case of Markov chain Monte Carlo. To start, I give first an example of that, and this is a very typical example from computer vision, and we had a similar problem already. I think we had this, the same problem we saw already when we talked about Markov random fields. Basically, what we have here is we have a problem that we would like to have. We assume we have a binary image. That means we have only pixels that are either +1 or -1. And now we would like to denoise that image. That means we have some noise on the image. We have some samples or points that are wrong there, and we'd like to remove the noise from this image. And the way we can do this is express this whole thing again with the Markov random field here, right? And the Markov random field is defined, as we said this already, with node potentials and edge potentials, right? And this is the very simple case, which is the Ising model, where we just have a binary case, and the Ising model simply describes pairwise potentials for adjacent nodes in the graph. That means these two nodes here, xs and xt, these are the latent variables of our model. These are the states variables that can have state 1 or 2, 1 or -1, sorry. And the blue ones are the observations. This is the actual pixel that we measure, right? And now we'd like to find the optimal states of the latent variables so that the noise is removed, right? So that is, and we have two potentials. One says that the latent variable is very close to the observation, and this model is a Gaussian. So we say if we know that we're in state 1 or -1, then the probability of measuring that what we actually measured, which is our yt, is a Gaussian, and we assume that we know the variance of that Gaussian, right? So this is the local evidence of observing this the observation. And now we have this edge potentials here, which simply says if two edges have the same label, then this has a higher potential than if they have different labels, right? So this J thing is a parameter again that we assume we know from the algorithm, and this exponential here simply says if xs and xt have the same sign, then this is a high potential, and otherwise this is a low potential, right? And now what we can do is we can now compute the probability, like for every node xs or xt. We can say what's the probability of xt given the probability of all the others, right? And we write this as x minus t. And we assume that we know the parameter theta. Theta is, where is it theta? Should be j. Well, for the moment, I don't consider the parameters. It's much more that's easy to understand like this here. This is what we call the full conditional, right? We condition the current variable on all the others. And what we have seen already is that this is nothing else than, we have the normalizer here. This is nothing else than the probability. We just have to multiply all the potentials, all the edge potentials and the node potentials, but only those for the neighbors. Why is that for the neighbors? Because the neighbors are the Markov blanket in this case. And the Markov blanket, as we have an undirected graphical model, the Markov blanket in the undirected graphical model is just the direct neighbors of xt. That means we only do the multiplication over all s, which are neighbors of t. N of t is neighbors of t. And we multiply the potential xs, xt, and we multiply that with the local evidence, which is simply xt, right? This is our Gaussian. This we know, right? We can just plug this in, psi of xt, and this is the edge potential that tells us how strong these edges are. How yeah, it's probably also better to think of this as the support, or how much support I get from my neighbors, right? Yeah, and to do that, we now have to compute the normalizer. And for the particular case that we have right now, it's quite a simple case, because we only have to look into the case that xt is -1 or +1. That means the probability, let's write it explicit, the probability that xt equals +1, given all the rest, is the potential over all neighbors of n of t times the potential of xs and 1 times psi of 1, right? We just plug in 1 for xt, right? We just want to have the probability that xt is 1. And the normalizer is simply that, right? Plus this where we switch from 1 to -1. So this is just, again, our product, like this, psi xs 1 psi of 1, plus where copy just this whole thing where we have now xs -1 times, right? So this is a particularly easy case. Sorry, this is xs. And this is the s over all neighbors of t, right? And now we can plug in our potential, right? Now we say these are the exponentials. We say let's do this apart. So we replace the product over all neighbors of t of exponential of j of xs and 1, right? Xt is now 1. This can be expressed now. This is the same as, we can now express this as a sum. We say this is exponential of j of the sum over all neighbors of xs, right? Just switch product and sum again. And this now can be expressed as, we replace this with some value called eta, right? This is just the sum over all latent states of the neighbors of t. And these can only be 1 or -1, right? The interpretation of this is that this sum is simply summing up all the, like, let's say we know the latent states of the neighbors, right? We say this is 1, this is -1, this is 1, this is -1. Background, foreground, right? This is a binary image. We have background and foreground. And let's say we know all these neighbors. Then we can interpret this sum as kind of a voting. Like that means that these two neighbors, for example, they say, hey, I'm background, you should be background too. And these two say, hey, I'm foreground, you should be foreground too. And if that's the case, then this would be 0, right? The sum here would be 0 because you just sum it up. So they have the same number of votes that say foreground as you have votes for the background, and then this, in this case, this is 0, right? And the exponential of 0 is 1, right? Then this would be just the equal case. Okay, and now we can express that. Yeah, so you can imagine that you can now plug this in here and here and here, right? You just instead of this product, you write it always with this exponential. That means that this product here is nothing else than exponential of j eta times our local evidence divided by exponential j eta local evidence plus exponential of minus j eta times local evidence of -1, right? This is just to normalize it over the cases. And this can be expressed now, and we had this already, with the sigmoid function. The logistic sigmoid function is defined as exponential of a times exponential of a plus exponential of minus a. And now we just have this factor in front, and it turns out this can be expressed as 2 j eta plus, and you have minus logarithm of this fraction here, right? So this is all you have to do, right? Now you can write the probability of this state xt given all the others as a sigmoid over this this expression here, right? This is then easy to compute. And now the algorithm is very simple. Now you just have a very big for loop over all pixels. For every pixel, you compute the probability and you sample a new state of that pixel with that probability. And you do this over and over again, right? And this is the the result. So here, this is after one sampling, right? Once you go over the whole image and you sample, and after 5 samples, it looks like this. And after like 15 samples, you get quite a good noise reduction of this already, right? Because you sampled from that distribution here, right? You have a proper distribution that tell you where foreground background is, and with that you can get rid of the noise. It's kind of an interesting thing to do. This is like the real application of sampling to a vision problem.
It looks like that's really fast.
Yes, it's yeah, that's easy to do. Yeah, that's right. It's a fast algorithm. Okay. Another example is, again, our Gaussian mixture models. Here we have to do a little bit math before, but this is basically what we had already. So the first thing you do if you want to do this Gaussian mixture model, you have this big joint distribution here, and you again express it in a full Bayesian way. In this case, it's not exactly the conjugate prior, it's a so-called semi-conjugate prior, which is slightly different from the conjugate prior, but this is not so much of a difference. So the difference here is only that the product here, this is a product of a Gaussian and an inverse Wishart, and it's not the real normal inverse Wishart distribution, but it's only a very minor difference here. I just take this from the book as it is from the books, but the main idea of what you need to know here is the first thing you do is you factorize that the same way. So we have a Gaussian here. You have, this is your multinomial distribution for the hidden variable z, right? Z just tells you which Gaussian you choose for a given parameter pi. Pi is the prior. This is p of pi. This is the prior for your multinomial, which is a Dirichlet distribution, right? Pi should be a Dirichlet distribution. So that the posterior is again a bit Dirichlet, and this is again your prior of mu and sigma for all the Gaussians, right? We had this already when we did variational inference for the Gaussian mixture model, where we had for every parameter in the model, right? This is parameter mu, sigma, and z. For each of these parameters, we have a prior distribution, right? Well, z is not a parameter, that is a hidden variable, but the hidden variable itself has a parameter, and for that we have a prior, right? So that means that we can express that in this way, and then from this expression it can be shown. Now the trick is to express this joint, or come from this joint to a full conditional, where we look at every little variable in this formulation here, condition on all the rest, right? Probability of this variable given all the rest. I'm not going through detail. This is math that you would have to do then to be able to run this algorithm. But you can show that this works, right? You can have this probability is proportional to Gaussian times the weight of that Gaussian. This is the Dirichlet distribution. This is the linear Gaussian case where you can see this is again a Gaussian here, right? This is the prior of my mu's, and it's the prior of the sigmas, which is the inverse Vischer distribution, which is a distribution over matrices. But this is all you need, right? What you have to do now is you have to implement sample algorithms that sample from these distributions here, right? Now you need a Gaussian sampler, a Dirichlet sampler, a sampler that samples from this here, which is also basically Gaussian, and something that samples from this, right? And then just go again of this big for loop. You just go through all the variables in every case, in every step. You sample from this, take that sample, plug it in here, sample from Dirichlet, plug it in here, and then you do Gibbs sampling on that. And it works quite nicely. This is what I did actually. This is my own implementation of that stuff, and it's impressive, right? It does only some sampling stuff and it does clustering, right? It's just really amazing how this works. So first we initialize the variable somehow, and the theory says that it doesn't really matter how you initialize it, right? Because eventually it reaches the stationary distribution, and then you reach then you can directly read off from the parameters that you estimated from the mixture of Gaussians. You can get the mean and the sigma, right? And this is where you can see the way, right? The path that it followed. It started here and went here and then split up, right? So both mu's and sigmas started here at the same position, and then they went here and then they split up. One went to the up and the other one went down, and this was just a couple of rounds to find this, right? An important question, of course, is how often do we have to sample? Here, what we can plot, of course, all 4 parameters, mu and sigma, for both Gaussians, and you can see how they change, right? And this indicates that in this particular case, after 50 samples, you already have quite a good estimate, because after that, nothing changes anymore. It just really stays very, very stable. In general, what you can do is you can use this mixing time t epsilon, which is the time that you can compute or this burn-in time that you need also is related to the eigengap, right? So what you can do is you can compute the eigenvalues of the transition matrix and then look at the first 2, and gamma is the distance between these first 2, and then you can say that there's a theorem that says this mixing time, the time that you need to sample at least, is not more than this expression here, right? Right. This is just to have an estimate of how long you have to wait until you have a stable distribution here, right? Once you have your transition matrix given. And now, this last thing is just to show that we have that Gibbs sampling is actually a special case of Metropolis-Hastings. How can we see this? First of all, if we say that our proposal distribution in Gibbs sampling is this here, then we will see that this is actually the case. Why is this the case? Well, this Q, what is this? This is the probability, this is our full conditional, right? The probability of X given all the others. And we multiply that with the indicator function. That means if we have 2 different sequences of variables, then our proposal distribution is exactly then the one for the Gibbs sampling if we keep all other variables, other ones than I, and only sample from I, right? This is the expression how we can now formalize that mathematically. We can say, in our particular case, this would be the proposal distribution for in the Markov chain, right? This is our Q. And now we can compute the acceptance rate, right? The acceptance rate alpha of our Metropolis-Hastings algorithm, which is definition here, where this is defined like this here. And the first thing we do now is we express the joint over all x prime or all x as the conditional times the prior, right? So we have, this is basically exactly the same here, right? Pi prime given all the rest primes times the rest primes is exactly the same as p of x prime, right? We just plug this is just the standard rule for conditional probability here, right? This q, where is the q? I think we just plugged. There's one step missing, I think. I think I'm missing one step. Yes, I think, yeah. The q is replaced by this p, right? That's right. Yeah, sorry. So we've replaced the first term by this joint, by this probability conditional times the prior on the rest, and we replace q by this here, right? Right? Where we just say we know that this is the same, right? This I function can be cancelled out, right? And now we can cancel. Now we can observe. Important is now to observe that all the primes. So this p of x prime minus I is the same as p of x minus I without the prime, because it hasn't changed, right? All the others haven't changed here. This is the same here. This hasn't changed. What then remains is also this hasn't changed, right? This is again the same as x. Now we have x prime given x, which is the same as here. We cancel this out against this, and we cancel this out against this, and this against this. So we cancel out of a cross. And what remains is 1. So the acceptance rate of this is 1. We never reject. Right? Gibbs sampling is the same as Metropolis-Hastings, with the difference that we never reject the sample. However, of course, even though the acceptance rate is 100%, it's not much faster, because we only sample every variable at a time, right? Not in general. In the MH algorithm, we can sample many variables at the same time. Here we have just take one variable, another variable, and this takes a lot of time too. So it's not much faster. But you can see this is a special case of MH. And this is just to summarize this. The MCMC algorithm is a family of sampling algorithms that can sample from arbitrary distributions by moving in the state space. And the idea is to have a proposal distribution that samples from one state to the other state, and then we have an acceptance probability that is computed with the target distribution and the proposal distribution. The most used methods in MCMC are MH, Metropolis-Hastings, and the Gibbs sampling method. And here in MH, we use the proposal distribution, and we accept a proposed state randomly. So we first, very similar to rejection sampling, we compute the acceptance probability and then sample. And if we accept, then we stay in the state. Otherwise, we reject the state. And Gibbs sampling does not do that, right? It never rejects. But in turn, what it does is it samples from the full conditional. So it takes every variable in turn and samples from that distribution. Okay.